All right, good evening, everybody. Okay, so we want to look at semiconductor this evening. Okay, semiconductor and electronics. Right. So now, what is a semiconductor? Um. All right. So a semiconductor is a property, right, or is a substance whose property lies in between the conductor and the insulator, right? So the property of a semiconductor lies in between the conductor and insulator. So in the groups of an element, when you have hydrogen, helium, you have lithium, beryllium, you have boron, you have carbon, you have nitrogen, oxygen, fluorine, you have neon, you have sodium, you have magnesium, you have aluminum, you have silicon, you have phosphorus, you have sulfur, you have chlorine, you have argon, you have potassium and calcium. Okay, these are metals. 1 to 3 is usually metals. All right, then this is what we call the metalloids. All right, metalloids or the semiconductor, because their property lies in between the conductor and these ones are the insulator. This is the rare atomic gas, which is the group 0 or the group 8 element. So, all right, their property lies in between the conductor and the semiconductor. Okay, so that's the first thing you should know about semiconductor. All right, now the examples, all right, they're also called metalloid, and the examples are carbon and silicon. So now there's what we call the energy band theorem. Energy band theorem. All right, energy band theorem. So in the energy band theorem, what we are looking at is the effect of your conduction band, all right, and valence band in the three different substances we have: conduction band and valence band. In the three different substances we have in physics. All right, so the materials are going to be considering, or the substance are going to be considering. The first one is, what is the effect of, these are the two energy band theorem in semiconductor. We have the conduction band and we have the valence band, all right, the valence band. So what is the effect of these two energy theorem in conductor, number one? All right, what is the effect of it in an insulator, or let's say in semiconductor, and what is the effect of it also in an insulator? All right, so that is the next thing we want to look at. We have talked about the definition of semiconductor. So now in the energy band theorem, so let's look at the essence, all right, or the effect of your conduction band and valence band in conductor. So at the conductor, what happened is that your conduction band and valence band, all right, are actually let me say they are linked together, or they are joined together, right? Both the conduction band and the valence band, all right, are linked on what? Or joined to this conduction band and this valence band, all right? And electrical conduction actually occurs, all right, at the conductor, all right? So the valence band and the conduction band and the valence band are joined together, all right, or we can say that they overlap each other, all right. At the effect of the two, of the conduction band and valence band at the conductor, all right, is that at the in the material in the conductor, all right, or at the conduction band, both the conduction band and the valence band at conductor, both the conduction band and the valence band overlaps each other, all right, so that free electrons are able to migrate from one energy level to another energy level. So there's an overlapping, all right, of the two energy theorem and the conduction, all right, at the conductor. And I said that electrical, all right, conduction actually occurs, all right, in conductor. Then number two, what happens at the insulator, all right? At the semiconductor, what also happens? So at the insulator, or at the semiconductor, first of all, the valence band and the conduction band are separated by what we call a forbidden gap, all right, but not as in insulation, all right. So the effect of that is that at semiconductor now, all right, there's a separation of these two energy theorem. We have our conduction band here and we have our valence band. So now this is it, and there's a small gap, all right, that is separated by this. So here there's an overlapping of of both the conduction band and the valence band, but here it is separated by what? A little gap, all right. So electrical conduction can also occur at the semiconductor, all right, in the effect of the two energy band theorem in semiconductor, because here we can use doping to increase doping the process we call doping. I'm still going to talk about it to increase the conductivity so that we can have electrical conduction. So at semiconductor, electrical conduction can also occur, all right, by a process called doping in semiconductor. So that is that. Then at insulator, what the effect of the energy band theorem at the insulator? At the insulator, both the insulator and conduction band are widely separated. They are widely separated. So it's not like the separation that happens in semiconductor. So at insulator, there's a wide separation, all right, of both the conduction band and the what and the valence band. So this is your conduction band and this your valence band. So here electrical conduction cannot occur, all right. Electrical conduction cannot occur at the insulator. At the conductor, electrical conduction can occur. At the semiconductor, electrical conduction can also occur because there's a little gap that is separated, and we can use the doping to increase the conductivity of the effect of the two energy band theorem at semiconductor. But insulator, they are widely separated by a gap we call the forbidden gap or the forbidden region. So electrical conduction cannot occur. The reason is because electron does not have sufficient energy to migrate, all right, or by jumping, all right, from this place by jumping the forbidden gap. The electron does not have that energy, that ability, all right, or the strength to migrate the forbidden gap. So there is no electrical conduction at the insulator. So to enhance the conduction at the electron must be given what we call a thermal agitation. Okay, then that is that. So let's look at the molecular structure of semiconductor. Now, when we talk about the molecular structure of semiconductor, what are the things we are talking about? Now, we have said that silicon, all right, carbon is an example of semiconductor. Germanium is also an example of semiconductor. Okay, silicon and germanium are tetravalent elements. Okay, then now in the molecular structure of semiconductor, there are two things we are going to be talking about. The first one is what we call the free moving electron. There's what we call free moving electron, and there's what we call holes. All right. Now these two things are what we call charge carriers. Okay. Now this is what we call molecular structure of what? Of semiconductor. So now I said that silicon, germanium, all right, carbon are all examples of what? Of semiconductor, and I talked about the two different charge carriers we have, all right. Charge carriers in semiconductors, we have free moving electron, which is negative, and holes is what? Is positive, all right. Those are the charge carriers in semiconductor. Okay, charge carriers, we call them charge carriers in semiconductor. The first one is called free moving. In the molecular structure of semiconductor, we have these charge carriers. We have free moving electron, all right, and we have what? Holes. Free moving electron, I said they are negative, while holes are positive. So when an electron migrates from one level, all right, one energy level to another, it creates what we call a hole, all right, and the holes are positive while the free moving electrons are negative. All right, so once that has been gotten, so what is doping? Once we said that to readily increase the conductivity of the material at the semiconductor or the effect of the two energy band theorem at semiconductor, we use doping. What is doping? So let us look at doping. Doping is the addition, all right, or is defined as the addition of impurities such as trivalent elements, e.g. boron, all right. Impurities, the addition of impurities such as trivalent elements, e.g. boron, all right, or pentavalent elements, e.g. phosphorus or arsenic. Okay, phosphorus and arsenic are pentavalent elements, while boron is a trivalent element. So the addition of both, all right, of either trivalent or pentavalent elements, all right, in a very small quantity to a pure semiconductor, all right. Your boron is trivalent, I said, while your phosphorus and arsenic is pentavalent. So the addition of any of these elements in a very small quantity to a pure semiconductor in order to increase its conductivity is what we call doping. All right. So doping is defined as the addition of trivalent elements or pentavalent elements to a pure semiconductor in small quantity to a pure semiconductor in order to increase its conductivity. So that is what we have at that. Okay. So it's very simple. So there are two types of semiconductor. Quickly, there's what we call intrinsic semiconductor, and there's what we call extrinsic semiconductor. Intrinsic, all right, we have intrinsic, and we have extrinsic. So in the next video, we're going to talk about more on that, all right. So these are the two types of semiconductor, right? We have intrinsic semiconductor and we have extrinsic semiconductor, all right. So we do analysis on that, all right, and in the next video. All right, thanks for watching and God bless you. Okay, bye.